A fundamental assumption of any comparative or quantitative analysis is that the data being analyzed comes from the same statistical population. For most spatial geologic information, we may assume slowly varying aggregate statistics. These assumptions permit us to compare and to derive relevant models of subsurface reservoir geology from well to well, as long as the well data are laterally consistent. That said, a very common situation occurs with well log data in that the logs are not statistically consistent or slowly varying. This is easily observed in well-to-well cross-sections, particularly with gamma ray logs. The inconsistencies arise from the differences in logging operators, logging tools, technology improvements or changes over time, log digitization and processing, and so forth. Methods to normalize well logs are well known. However, the procedures are often tedious and in themselves inconsistent from well to well, especially when performed by different persons within a given study area. These areas of interest may contain tens, if not hundreds, of thousands of wells. To analyze and correct as necessary logs on a well-by-well basis from so many wells is not practical and often not achievable within the time frame of a given business opportunity. A customer to whom I gave a demonstration of this utility said, "It costs us about $300 per log to have it normalized, and we can get perhaps 4 or 5 normalized per day. More often than not, we only have time to normalize those logs needing the most correction. We know it compromises our analyses, but we just don't have any alternative." In concept, normalization is quite easy, but why is it so difficult in practice? Well, there are a number of important steps that are required. First, which of the many wells in our database have logs requiring normalization? Then, we need to identify which nearby wells with the same log type are to be used in building the target distributions required to normalize the logs identified in the first step. Performing the normalization of the source log to the histogram of the target logs is actually the easy part. What if it is deemed that different zones really require different normalization solutions? Multi-zonal normalization only compounds the required effort. DI Transform provides a solution to these difficulties by leveraging the power of the computer and statistical analyses. The results are quick and consistent, and the quality control tools and user oversight ensure they will be adequate and appropriate for further analytics and modeling. Let's explore the application and workflows by beginning with data selection and analysis. The study database for this tutorial focuses on the Wattenberg area of the Denver-Julesburg Basin. It is just northeast of Denver, Colorado, and consists of a subset of DI's DJ Basin Play Assessment. This subset contains 6,052 wells, in which each well has at least one gamma ray log. None of these logs have been previously normalized, and most consist of the original digital samples, although there are known issues with the data, as we shall see. Two cross-sections, roughly along depositional dip from southwest to northeast, and depositional strike from northwest to southeast, respectively, have been constructed to illustrate the need for some degree of normalization. We will first examine the dip line. It has been flattened on a regionally present event that will define the top of our zone to be used for the normalization. More about that in a moment. The zone of multiple events near the bottom of the cross-section is the late Cretaceous Niobrara-Codell sequences. The events comprise the A, B, C chalk benches, Fort Hays limestone, and the Codell sandstone. These are the primary zones of oil and gas interest in this part of the basin. The green event, on which the cross-section is flattened, and the pink event below it, were specifically interpreted for normalization purposes. There are a number of opinions on how best to normalize logs. The two most common, and the Transform application permits both, are 1. Find a zone that is expected to be relatively homogeneous across the area of interest. Often this may be a shale, chalk, or evaporate interval that varies little in property characteristics. These intervals are usually of short time duration and may be relatively thin. The normalization algorithm ensures that the aggregate statistics from this interval across all well logs are nominally the same after processing. The assumption is that the shifting scaling parameters necessary to normalize the analysis zone are appropriate for normalizing the rest of the log. This may or may not be the case, but it is easily tested within Transform. The second approach is similar in concept to the first, but involves a larger zone of analysis and a slightly different assumption. Instead of concentrating on a zone that came from a single geologic setting, we'll look at a zone that represents a system of varied events. Within the context of the system, we assume that all events have occurred equally on average. The second approach is the one we've taken in this tutorial. The zone we've selected is within the Upper Cretaceous Pure Shale, which is composed primarily of fine siliciclastic facies. These tend to be highly cyclic or repetitive, both across the study area as well as localized within it. On average, any given location will contain roughly equivalent accumulation of all facies over this large interval. Also, there are bentonite beds that permit spatial correlation of time markers. In this cross-section, it is easily seen that baseline statistics over the zone, green to pink, are not stationary. Some severe vertical striping is present, notably in the middle and right side of the section. This striping is indicative that normalization should be performed for future quantitative work. Zooming in on a portion of the cross-section also clearly shows minor striping that should be mitigated. Imagining doing this normalization one well at a time. The severe ones would obviously be done first, but doing all of those necessary to properly balance the section might prove onerous. The strike line shows a similar degree of symptoms, suggesting the need for extensive normalization over the entire area. These two cross-sections only represent a small percentage of the entire well set. This means just the identification of all wells requiring normalization will be a daunting task, as noted in the reasons for a multi-well normalization approach. As a side note, it is strongly recommended that property display scaling in most graphics be fixed to the same min-max range. Otherwise, visual comparison can be substantially compromised. Here we've set the min-max range to 0 to 200 GAPI for every log track. As we'll be seeing later in the workflow, we will follow this recommendation to great effect. Another diagnostic tool for determining how balanced the selected property logs are across the study area is to generate maps of statistical attributes. This contour map, with an interval of 5 GAPI, is the median value over the green to pink zone. The log values were filtered to the range of 0 to 200 GAPI to avoid the influence of aberrant values in the logs. We will go through why this range was selected in just a moment. The color scale range has been set from 85 to 130 GAPI. This is much broader than we would expect for median values for this zone over this area. Also, note the spatially chaotic nature of high and low values, basically the bubbles in there, and no clear hint of a spatial trend. Our gamma ray logs definitely require normalization. To initiate the normalization tool, select the Log Normalization Multi-Well item under the Geologic main menu item. Depending on the number of wells and the number of well logs in your database, it may take a minute or so to populate the initial panels in the app. The view part for the multi-well log normalization is broken into two main sections. On the left, a table with well information and associated statistics and normalization solutions, and on the right, a multi-panel section consisting of 3 tabs: Log Normalization Setup, Results Map and Histogram, and Solution Panel. The table is always present, but the panel section is controlled by which tab has been selected. Begin by selecting the wellbore list from the pull-down combo widget that contains the wells you wish to consider for normalization. On selecting a well or wellbore list item, a filter is run to winnow as necessary the available log aliases or mnemonics. The Log Normalization Setup panel contains the selection mechanisms for the well log, either alias or mnemonic, and any well top aliases to define the analysis zone or zones. The lower portion is a histogram plot displaying the univariate distribution of the current data to be used in the normalization workflow. We select the well list by the name of Study Area Wells with GR, which was created with the Create Well List utility. This list contains 6,052 wells that are within the area of interest and possess a gamma ray log. Then we select the gamma ray log alias and the normalization top and normalization base well top aliases. If we don't select any tops, then the analysis will use the entire log. This most likely will violate both of the two assumptions we discussed earlier, because most logs do not have the same total zone of coverage. It is, however, an option to do so, but if this is not what you want to do, then at least two top aliases must be selected. Selecting more than two then defines more than one zone and puts the tool in multi-zone mode. After selecting the actual wellbores to use, here all of them, we see that the Retrieve Log Data button at the bottom is now enabled. If it isn't, check that a log alias or mnemonic and that either none or two or more top aliases are selected. Upon pressing this button, data for the selected log from the selected wells over the specified zone or zones are fetched from the database, and the histogram for the retrieved log samples is generated and displayed. For our selections that we made, we see that the minimum and maximum log values found are minus 999.99 and 940.71. Certainly we don't expect negative numbers, and the minus 999.99 looks suspiciously like null values were imported originally to the database. Also, we see that the upper tail has very few samples above 200. We could go back and reload the logs or use the log calculator to perform some cleanup, but for now, we'll set a filter from 0 to 200 GAPI using the range slider below the histogram. A quick way is to click with the right mouse button on the slider, which brings up a dialog. The lower numbers in this dialog are the values to filter, so we set them to 0 and 200 for the minimum and maximum respectively. Upon accepting these as the new data extremes using the OK button, we see that the filter is applied and the resulting histogram is much better behaved for analysis. Another thing to note is that some of the wells in the table have been deselected. These are the ones with the bullet icon instead of a check mark. This column may be sorted. Clicking twice on the header for that column sorts all the deselected wells to the top of the table. Scrolling to the far right makes the comment column visible. We see for each deselected well the reason why. In most cases, the well did not have the complete set of top aliases we selected. The number of available wells with log values for the normalization analysis has now been reduced to 5654. Like we suggested with going back to the log cleanup, you can create a well list of these rejected wells and see if additional interpretation of the necessary tops can be made. For demonstration purposes, we will proceed with what we have. The next step is to compute the univariate statistics, mean, median, standard deviation, p-lower and p-upper values for the data from each of the remaining wells. This is done by pressing the Compute Statistics button. Upon completion of these computations, a map of the median values interpolated using each well value is shown. Note the two combo boxes at the top of the map. The left indicates original and the right median. One can also see the p-lower and p-upper maps. We will compare these original maps to subsequent control and normalized solutions for quality control purposes. It is also useful to look at the well log statistics in the table. Two columns in particular are potentially informative in finding problematic well logs we may wish to eliminate from the analysis. The first, the number of samples, and the second, the standard deviation of the samples. A small number of samples may indicate gaps in the logs that can compromise the zonal statistics. Sorting the number samples column from small to large and examining those with small numbers can illustrate the logs with gaps. Clicking on each row displays the log values and associated histogram. Those with obvious recording or digitization gaps are deselected. A similar process of sorting with the original standard deviation column is a good diagnostic tool. Small standard deviations may mean that a gap in the log has been filled with constant values. This will also lead to a spike or spikes in the associated histogram. These logs too are deselected from the analysis. Upon deselecting those wells with logs that contain potentially compromising issues to the normalization process, it is necessary to recompute the statistics before continuing to define the control wells. Control wells are wells which contain logs that require no normalization and will form the initial basis for the normalization algorithm. In comparing the various gamma ray maps to each other, it is often useful to turn off any autoscaling and to fix the minimum and maximum values of the color scale. This is done by a right mouse click on the map, unchecking autoscale, and then setting the minimum and maximum values. For this demonstration, these are set at 85 and 130 GAPI respectively. The blue arrow in the upper left corner of the Results Map panel controls the expanding of a panel for the control and normalization parameters. The first of the parameters that is significant determines which wells will be control wells. The topic of control wells is discussed in the next section. Control wells are the wells for which their logs have been determined to not require normalization. This determination is made using the distributions of the median, p-lower, and p-upper values obtained when the statistics were computed. These are also the wells that have the logs which are to be used to initialize the normalization algorithm. These distributions may be seen in the histogram plots under each of the original maps. The p-lower and p-upper values are defined in the panel, defaulted to p10 and p90 unless you've changed them. Each of these distributions has a mean and a standard deviation. A well can only be considered a control well if its median, p-lower, and p-upper value falls within the range defined by the mean plus or minus the scaling coefficient specified on the parameter panel times the respective standard deviation. A value of 1 means that about 2/3 of the wells will pass. The smaller the coefficient, the fewer number the wells that will pass. For a well to be assigned as a control well, it must pass all 3 filters. After pressing Control Wellbores button, the map will update as the coefficient value in the slider widget is changed. A good value is one where the resulting map contains a reasonable or expected trend. Remember, it's a good idea to fix the minimum and maximum values of the color scale and that the autoscale option is off. Here, after pressing the Control Wellbores button with the coefficient slider at 1, we see the map of interpolated median values for the resulting control wells. As the slider is moved to the left, defining smaller coefficient values, the number of control wells also decreases. The map becomes smoother as the range of passing median values narrows. Also, observe the range of values in the associated histogram below the map. Zooming in on the map better shows that the control wells are displayed as green symbols. Non-control wells that are candidates for normalization are still shown in black. Ideally, we would not only like to capture the expected trend in median gamma ray for the analysis zone, but the spatial distribution of the control wells should be nicely spaced and not too clustered. Besides being displayed in green in the base map, control wells are also labeled in the table. The control column may be sorted so as to congregate all of the control wells at the top of the table. It becomes easy then to cycle through the logs to check that we won't be using logs that might prove problematic or compromising in the normalization analysis. These wells are the ones used initially in the normalization process and have aggregating contributions as the process proceeds. More on this in the next section. In our example, there are 589 control wells from the 5,642 total wells, or a little over 10%. We are now ready to run the normalization process. Before we discuss the multi-well process flow, let's first review the basic normalization step for any given well log. For this well log to be normalized, it is first necessary to establish a target distribution to which the current well log distribution will be matched or normalized. This matching requires the determination of normalization scalars, shift and/or stretch or squeeze, as required by the selected normalization option. Normalizing begins by generating the well log's univariate distribution. We call this the source distribution, and identifying up to 3 locations along that distribution: the median value, specified P lower value, and specified P upper value. The P lower is defaulted at P10, and the P upper is defaulted at P90. These may be changed as appropriate. These same 3 locations are identified in the target distribution. How we derive this target distribution will be discussed shortly. For now, let's discuss the 3 options provided for matching the source histogram to this target histogram. The first option is the median shift only. This is a simple shift of the source distribution so that the resulting distribution has the same median as the target distribution. The shift is the difference between median values of the source and target distributions. This difference is applied to every value in the source log. Hence, the resulting normalized log has the same median as the target distribution. The median shift-only method does nothing to the shape of the newly formed distribution. It remains the same as the input distribution. Depending on the similarity or dissimilarity between source and target distributions, this may or may not be desired. In order to address differences in the shape of the source distribution to that of the target distribution, it is necessary to compute a stretching or squeezing scalar, or scalars depending on the option selected. The most commonly described method in the literature uses the P lower and P upper values of the source, denoted by S, and target, denoted by T, distributions. A scaling coefficient is computed as the ratio of the target range, that is P upper minus P lower of the target distribution, to the source range, P upper minus P lower of the source distribution. This ratio is applied to each log value in S using the equation shown here. This method anchors the source distribution to the P lower and P upper values of the target distribution, but it doesn't ensure that they have the same median. The drawback using this option, where the median values might not be close, is that the human eye can easily see this difference in cross-sections. A slight modification to this equation will ensure that the resulting distribution of the normalized log will have the same median value and the same range from P upper to P lower, although it won't necessarily be exactly anchored at the same P lower and P upper values. Instead of referencing the log values at P lower, we'll reference them to the median. This new equation is shown. This method assumes that the ranges of the tails from the median of the distributions are the same. In other words, the distribution is pseudo-symmetric. That is, the median value minus the P lower value is the same as the P upper value minus the median value. Often, the log property distributions are not symmetrical in this regard, and that the degree of asymmetry is different between source and target distributions. In order to handle such asymmetry, a third option, and the default one, is provided. To achieve this, we split the previous equation at the median and use different scaling ratios from P lower to median and from median to P upper. Now we have the two equations as shown. In practice, we found this to be the best option, hence why it is the default. It still handles symmetry, for the scaling ratio of the lower tail will be nearly equal to the scaling ratio for the upper tail, but it handles asymmetric situations where they can be quite different. Now that we've covered how an individual well log is normalized, let's discuss how this works in a multi-well approach. In essence, it comes down to what order the well logs are to be normalized and what well logs contribute to the associated target distribution. The order is defined by creating a priority queue of well logs that require normalization. Priority here is defined as the logs requiring least amount of normalization be addressed first, to those requiring the most amount last. The amount of normalization is defined by going back to the global distributions of median, P lower, and P upper for all the well logs. The standard deviate or z-score for each of these three locations are summed for each well, and then these sums are sorted from smallest to largest to generate the priority queue. Now we are ready to loop through the queue, starting with the first wellbore in the sorted order. Using the specified search parameters, find the nearest control wellbores from which to generate the target histogram. For the first wellbore in the priority queue, only control wellbores are available as possible contributors to this target distribution. Upon finding any wellbores in the search, generate the target histogram from these respective well logs. Depending on the selected normalization option, then normalize the source well to this target distribution. Add this wellbore to the available control wellbores and use its normalized log in any subsequent target distribution. Go to the next wellbore in the priority queue. By adding each wellbore that's been normalized to the control wellbores permits a smooth propagation of any trend in the well log statistics. This is further affected by going from wellbore requiring lesser adjustment to those requiring the most adjustment. Now, let's normalize our well logs in this tutorial. The first step is to define the type of search we would like the process to follow in finding nearby control wells for determining the target histogram. There are three parameters: the type of radial search binning, in other words, quadrant, octant, 16, and so forth, the maximum number of wellbores for each search bin, and how far away the search should look. In our example, we are using an octant search with a maximum of 3 wellbores per octant, no more than 15,000 feet away. This means there could be as many as 24 well logs contributing to a given target distribution. The next step is to select which normalization option to apply. Here we are taking the default of two-tail scaling. Finally, we may wish to change the values defining P lower and P upper allocations in the normalization equation. Again, we are accepting the defaults of P10 and P90. That's it. We're ready to run the algorithm by pressing the Perform Normalization button. The process is really quite quick, even when normalizing nearly 5,000 well logs. For brevity, the clip speed has been increased by 4 times. Upon completion of the normalization loop, the median map is updated to reflect both the control median values and the median values of the newly normalized logs. Switching back and forth between the control-only map and the normalized map shows that the desired trend has been maintained, and the resulting histogram looks like the control-only histogram. The locations of wellbores that have been normalized are displayed in the base map using a red symbol. Note that there are still a few locations colored in black, meaning that they did not get normalized, nor are they a control well. They tend to be on the fringe of the well control and are not closer than 15,000 feet from any other well. Should one wish to have these normalized, the maximum search distance will need to be increased. We can map and show the histogram for each of the solution scalars, shift and p lower scalar and p upper scalar. There are anomalous scalars in both the p lower and p upper that stretch up to 4 and 14 times respectively. We will investigate those solutions shortly for problematic data or conditioning. The wells with logs that have been normalized are so annotated in red in the table under the control column. Sorting this column enables easy identification of control wells in green, wells with logs normalized in red, and the remaining wells whose logs weren't normalized, no color. Standard table options permit easy construction of well lists for future reference. Let's look at the solutions with abnormally large scaling factors. This is easily done by sorting the solution scalar columns, specifically the p upper. One can easily move through the solution panel to show the original log versus the normal log and to display the logs from which the associated target distribution was constructed. Moreover, the original and normalized distributions are shown along with the target distribution and the individual control distribution to the target distribution for the reference wells. In a number of these solutions, constant values are filling gaps, creating spikes in the source histogram. These wells were not previously caught and deselected. We do so now. Looking at the index of these wells in the priority queue shows that some of them were quite early in the process flow. This means that these solutions most likely affected well logs normalized later in the loop. To examine the well log values that comprise the target histogram for any given solution, click on the ellipsis button next to the named reference log. A dialog appears containing each of the target well logs, and you can easily cycle through them. The associated reference histogram and overall target histogram are shown in the lowermost plot. After deselecting them, it's a simple matter of rerunning the statistics, control wells, and normalization. Looking at the subsequent solution scalar maps show much better solution scalars. Let's go ahead and create the normalized logs and persist them in the database. This is accomplished by pressing the Create Logs button. A dialog appears that permits us to specify a new mnemonic name for the normalized gamma ray logs. To apply the solutions to either the entire log or just the zone or zones on which the analysis was performed, whether to assign the new mnemonic to the top of the priority list in the associated well log alias, and finally, whether to create the log only when the mnemonic doesn't exist or to overwrite any existing logs by the same name. Now we're ready to look at the results in the context of the two cross-sections we created in the Introduction and Setup section. We have the southwest-northeast depositional dip line and the northwest-southeast depositional strike line. For each, the original logs are displayed, followed by the same section, but after the normalization process. Here is the first cross-section with the original logs and then the final logs. The improvement is quite striking. The same improvement is seen in the second cross-section. In a short amount of time and with little effort, we have nicely balanced the gamma ray logs. They are now ready for further interpretation and quantitative analyses. We have saved ourselves much work and time, and as follows, money, by allowing statistics and the power of the computer to control this process. These savings only compound if a multi-zonal approach is warranted.